Good day, ladies and gentlemen, and welcome, one and all, to Encyclopedia Hermetica, Part 43. So, today we're going to take a break from the Punic Wars, and just to change things up, we're going to stop and take a look at Hellenistic natural philosophy, which is the kind of natural philosophy which would eventually become co-opted by the Greeks, Roman conquerors, and brought into the fold of empire. So, to talk about Hellenistic quote-unquote science is to talk about Roman quote-unquote science. In order to discuss this subject coherently, however, I'll need to break with our chronology to rewind time a little and put things into perspective. Now, just before I jump in, I'll give a word on why we should discuss this within the context of Hermeticism. Well, the fact is, Hellenistic natural philosophy has everything to do with Hermeticism, especially when it comes to the Hermetic grimoires which floated around in late antiquity, in the Islamic world, and in Latin Christendom. And I'm not talking about this namby-pamby New Age, the Emerald Tablet is about the secret kind of Hermeticism either. I'm talking about the real deal historically. What ancient and medieval wizards actually believed and were interested in, which by and large was the quote-unquote science of the day. I spent a good chunk of the last 4 years of my life co-authoring a scholarly translation of the Latin Hermetic grimoire, the Picatrix, which, I might add, is currently done and under peer review. And believe you me, if you don't have a basic grasp of Hellenistic science, all of it would seem like just incoherent psychobabble. Magic, philosophy, religion, science, all of these things were inextricably intertwined with one another in the ancient world. Aristotle and Hellenistic natural philosophy, in its cosmology, in its understanding of the human body, in its conception of matter, and so forth, would endure with their quasi-functional systems, with the help of the literate, until the scientific revolution started gaining momentum around the 16th century, with discoveries of folks like Paracelsus and Copernicus. And I don't want to be dismissive of these old systems either. These were functional models. They worked quite well until they didn't. And when they didn't work, they were adapted to accommodate for inadequacies. Something like epicycles comes to mind. They aren't objectively real phenomena, but if we look at the planets from an anthropocentric view, we can see the epicycles are necessary if we actually want to make any astronomical predictions without any recourse to a heliocentric model. So, with that said, I want to stress that Hellenistic natural philosophy was an enduring project. It was alive and green and always being adapted, constantly undergoing refinement and corrections. But that being said, I also don't want to understress the constant appeals to authority, which this system also depended upon for centuries. Historically, the weight of the ipse dixit fallacy in the manuscript tradition is actually stunningly sitting to how modern-day conspiracy theorists take all their quote-unquote research from one source, such as Zecharia Sitchin, at face value. That's what ipse dixit means in Latin. He said it himself. It's a dogmatic appeal to authority. You can find millions of people talking about, say, the Anunnaki forcing humans to mine gold thousands and thousands of years ago. But if you dig into the sources, every single one of them reference this one guy's translation and take it at face value solely because it's the alternative narrative. This is why historiographical projects are nice. They force you to dig deep until you hit the bottom, and what you find is that a good portion of the time, claims made by, say, antiquarians of the 19th century are often baseless or passed on with little supporting evidence. I'm sure you all know the type, the folks who claim things like, "The Emerald Tablet of Thoth is 10,000 years old and contains hidden wisdom from Atlantis," without a shred of evidence. And then you also get folks who claim the Emerald Tablet is an 8th century document about metallurgy in the tradition of Zosimus of Panopolis. And of course, nary the twain shall meet. Okay, so before moving on, I want to mention that I'm working with the help of a work by Lawrence Principe from Johns Hopkins University. I love this guy's material because he's both an historian and a professional chemist, so his specialty in the history of science is doubly deep. To me, it's refreshing to hear his sort of no-nonsense approach to things like alchemy, astrology, and so forth, because by and large, there's a real dearth of information on the history of these topics that isn't contaminated by occult speculations. And this Encyclopedia Hermetica of mine isn't exempt from this, of course. So, in any case, I highly recommend the books and lectures of Lawrence Principe. Now, it's impossible to discuss Hellenistic natural philosophy, the ancient world's equivalent to what we today would call science, without going back to Aristotle. Because it was Aristotle who not only developed a system of natural philosophy which would explode into popularity across the Mediterranean world, but also a method for carrying on his work where he'd left it. Let's not forget, it was Aristotle's very own disciple, Alexander the Great, who would subdue a huge portion of the world's population and bring it into the fold of Hellenistic thought. I mean, what better PR move for Aristotle could there be? Now, in 335 BC, after having been away from Athens for 12 years, Aristotle returned, and there he founded a school called the Lyceum. Aristotle had been a student under Plato for 20 years at the Academy, and so there was this precedent for founding schools in Athens, to say nothing of all the other schools of philosophy. Now, this school, in addition to its role in pedagogic pursuits, also served to further Aristotle's natural philosophical projects. Well, about a decade went by, and in 323 BC, Aristotle felt pressured to flee from Athens. Why, you might ask? Well, remember, this is the date of Alexander's death, so there was a lot of political turmoil in Athens as a result of this incident. Having been Alexander's very own teacher, he thought it best to dip out before anyone noticed him and got any funny ideas. There was just a really vigorous anti-Macedonian sentiment going on in Athens at the time, so Aristotle took his cue and got out, claiming that he would save the Athenians from the disgrace of committing their second crime against philosophy, the first, obviously, being the death of Socrates. Well, Aristotle didn't just leave the Lyceum in shambles. No, he entrusted it, rather, to one of his most faithful disciples, and a fellow student of Plato's, Theophrastus, often referred to as the father of botany. Now, Aristotle didn't really live much longer once he fled to Colchis in Euboea, so Theophrastus acquired full ownership over the Lyceum in 322 BC. which he then led for the next 36 years. A large portion of Theophrastus' work was devoted to expanding on Aristotle's, particularly his work on plants and on minerals. Work which would become foundational to all manner of alchemical pursuits. Theophrastus had one work which contained the descriptions of over 500 different plants, and in it we can see the Aristotelian method of categorizing and classifying being put to use. It was the same kind of format you'd see in Aristotle's History of Animals, or that is, enquiries concerning animals. Theophrastus also had a lapidary in the style to classify and categorize minerals. Now, Theophrastus disagreed with Aristotle on all manner of points, and this was a good sign that the wheels of thought were always turning from one generation to the next. For example, Theophrastus disagreed entirely with the idea that fire was one of the 4 elements. He believed it should just be in a category all on its own. More importantly, Theophrastus was a little more, let's say, nihilistic than Aristotle, in that he rejected the universality of final cause. He rejected teleology. Frankly, he thought there are things in life which have no purpose. And this really flew in the face of the whole Aristotelian notion of nature. Now, what triggered this deep sense of dark cosmic existential loneliness for Theophrastus? Nipples on men. I kid you not. There's no rhyme or reason, no final cause, no telos, behind men having nipples. Therefore, the universe has no intrinsic purpose. And I agree. Now, I'm only telling you this so you maintain this idea in your mind that Hellenistic natural philosophers were dynamic thinkers. They had their own agency. Many thought for themselves. With change being the only constant in the universe, Theophrastus died in 286 BC, and the third leader of the Lyceum to be selected was a kalos kagathos, a gentleman, or a man of leisure, if you will, named Strato of Lampsacus, who'd hold the post for the next 18 years. Now, unfortunately for us, nothing he wrote survives. Alas, what we do know is that he had the nickname Ho Physikos, the naturalist. So this at least gives us a sense of what his interests were. We know that Strato believed in something that Aristotle rejected, and that is a vacuum. Aristotle couldn't conceive void space, but Strato, by doing an experiment with a kind of brass balloon with a straw sticking out of it, he noticed that if you blew air into it, you could raise the pressure inside the balloon. Well, if he could add air to a system which was already full of air, where was the new air going? Well, this, to Strato, was proof that there must be void spaces left in the balloon, and the extra air added fills them up. Alternatively, he could suck all of the air out from that brass balloon, and then it became really evident that the air just rushed back in once you took your finger off the opening. So there must be a vacuum inside while it's sealed shut. Now, all this may suggest to you that Strato was an atomist. And we don't know if that's true for sure. But if it is, then we know that Strato has really diverged in the span of 3 generations from the quote-unquote pure original form of Aristotelian natural philosophy. Either way, it was this ability to criticize one's teachers, this ability to reject tradition, and not just on minor points either. This was the lifeblood of Hellenistic thought. From a literary standpoint, this was almost a prerequisite for being able to publish at this time, to show you've surpassed your predecessors and added something that they didn't already know. Science in the hands of agnostic Greeks flourished. There was no single authority who pontificated on how everything in the world is or ought to be. This conception of the world was very important. And I think that this emerged in part as a byproduct of Athens's political climate. There was a sort of democratization of thought at work, as opposed to standardization. Now, there are some people out there who like to think of the Hellenistic period as a sort of period of quote-unquote decline in terms of Greek philosophy and Greek culture in general. Whenever you hear decline, this should set off some red flags. To say that Hellenistic Greeks were inferior in some way to classical Greeks is nothing more than a matter of perspective. This is an opinion which can be traced back historiographically to the writers of the 19th century, who basically took all Greco-Roman canon at face value. There's a long history of maligning the Hellenistic period, and the idea was because they were derivative in thought to the classical Greeks, with the erroneous assumption that classical Greeks themselves were not derivative of those who came before them. Much of the work done in the Hellenistic period debated with and expanded upon the works of old masters who'd founded various schools of thought. Zeno, Epicurus, Plato, Aristotle, Pythagoras, and so forth. These are all figures that we've discussed. But just because those born during the Hellenistic period elaborated on some earlier sage's model doesn't mean that they themselves were any less deep of thinkers. Arguably, it takes even more strength of will to come up with a model that breaks a pre-existing mold than to start from scratch. A lot of what was going on was the practical application of a lot of the more speculative, theoretical stuff that these older sages had posited. So, let's talk about some of these things. Now, around 300 BC, the Museion of Alexandria, the temple to the Muses, was founded in Egypt, and as we've gone over in Lecture 33, Alexandria rapidly became a major cosmopolitan center and a hub for those with more intellectual leanings. The Museion and the attached library were funded by patronage. They received funding from the local government, essentially, and this was rather unusual for governments to fund scholarship. But it starts here. This was a matter of civic pride and of political glory. Being a lavish donor as a patron was the chief means of expressing one's goodwill to the world, and it also happened to be a great way of solidifying power structures. Though I suppose it's no different today, what with angel investing and huge philanthropic donations and that sort of thing. If I give you $1 million and I promise to give you another one in a year, you're likely to be partial toward my way of doing things. Now, Strato, the disciple of Theophrastus, who I just mentioned, apparently spent some time in Alexandria. Now, one of the most influential figures on history who would spend a lot of time in Alexandria as well, was Euclid the geometer. I mean, even his name means the famous one. Euclid is best known for his deductive and axiomatic statements about geometry. He wrote works on perspective, on spheres, on cones, on number theory, and on mathematical rigor. Euclid was active in Alexandria during the reign of Ptolemy I, 323 to 283 BC. And now, the funny thing is that I don't actually have to tell you much about Euclid, because unless you grew up in a third world country or were homeschooled by idiots, you probably have a basic grasp of Euclid's principles from high school math class, which is wholly based on the deductive and inductive proofs that are laid out by Euclid himself in his work called The Elements. Now, that being said, even if I wanted to tell you more about Euclid, I couldn't, because very little survives on Euclid specifically, except for bits and fragments here and there, and a work by Proclus, one of the great Neo-Platonists of late antiquity. So, let's skip over to another figure of interest to us, and that's Eratosthenes of Cyrene, whose dates are circa 276 BC to 195 BC. This guy, for a time, was the head of the library attached to the Museon, what some people called the Great Library of Alexandria. Though I'm reluctant to use that term because there were many libraries of Alexandria destroyed at various phases throughout history, and this tends to get compressed in people's minds as being one building of incalculable importance that was destroyed as a sort of assault on knowledge. So, for example, the first major case of library destruction wasn't an assault on knowledge so much as a warlord using fire to relieve a siege, a fire which quickly got out of hand. Now, one of Eratosthenes' greatest feats of intellect was his attempt to measure the size of the Earth, which, of course, everyone already knew to be round. His whole experiment was contingent on that fact. At some point in his life, he'd heard of a certain well down south in Egypt, where the modern town of Aswan is today. He'd heard that there was a very, very deep and dry well over there, and that on a single day of the year, a gnomon, or a stick, stuck into the ground to stand up vertically, cast no shadow whatsoever. Now, at the exact same time, on the exact same day, back in Alexandria, a gnomon stuck in the ground would cast a shadow. So what he decided to do was to measure the angle of the sun, how far the angle was being at the point of mid-heaven. With the help of basic geometry, he realized that the angle would be the same as the angle at the center of the Earth between a line stretching from the Alexandrian gnomon and the one in Upper Egypt. Next, he measured the distance between Alexandria and Aswan, then divided 360 degrees by the angle subtended between those sticks. He then multiplied that angle by the distance between the 2 points. So, after he did all this, what did he get? 250,000 stadia. Now, here's where the problem arises. We don't actually know how long Eratosthenes' stadia actually were. Weights and measures were not standardized in the ancient world, so we have no way of knowing how precise his measurement was. Now, if we take the average of a bunch of different stadia, we get about 10 stadia to a modern mile. So let's pretend as if this was actually the case for Eratosthenes, in which case we can say that that put him within 15% of the actual Earth's size. It's even possible he had it figured out to 2% of the actual size of the Earth, but there's no way of confirming this without knowing for sure how long Eratosthenes' stadia were. In any event, the errors arose from the technological limits of his measurements, not from the method that he devised. Alright, well, outside of Alexandria, there was a lot of action too on the intellectual front. In astronomy, one of the more important figures of the age was Hipparchus. One of the things that he did was compile an extensive star chart, recording their size, their brightness, their positions, and so forth. And even the chart modern astronomers use today is called the Hipparchus Catalog. Though in this case, we're talking about Hipparchus the satellite and not Hipparchus the man. Now, something that Hipparchus did that's about as astonishing as Eratosthenes' feat was to measure the distance between the Earth and the Moon. He knew he could do this because while a total eclipse could be seen over the Hellespont, the isthmus between Greece and Turkey, 1/5 of the disk remained unobscured over in Alexandria. Hipparchus, therefore, traced a giant triangle with its base linking Alexandria and the Hellespont, and its topmost point touching the Moon. Now, that very acute angle which touched the Moon had to be equal to the angle subtended by the visible portion of the Sun, i.e. 1/5 of its disk, which is equivalent to about 6 seconds of arc. From this, Hipparchus could estimate the height of the triangle as being 71 to 83 Earth radii. Later, he changed his final calculation to 62 to 72 Earth radii, and in comparison to the actual 60 Earth radii that exist between the Earth and the Moon that we know today, his answer was pretty damn good. Another crazy feat of his was to determine the length of a full lunar cycle to within 1 second of its currently accepted value. Which is roughly 28.5 days. I should add that he didn't do this alone. He made use of centuries worth of Babylonian records to make his calculations. So we could say that this was more of a trans-generational group project than the fruit of Hipparchus's labor alone. Now, what I want to point out here is that there is something about the ancient mind that the modern mind cannot grasp, at least in most people's cases. And I know that mind is not really the right word here, because this obviously includes physical bodily functions too. Our ability to focus, our attention spans, our patience, even our senses of hearing, of sight, and of taste, these have been entirely eroded by modern technology and standards of living. What makes a lot of these ancient sages so interesting is what seems to moderns to be an obsessive level of dedication to observation that very few of us have the patience for anymore. Loud noises, bright lights, sweet tastes, extremely fast-moving objects, these were all relatively absent from day-to-day life for the ancients, and this caused them to be much more sensitive to the world around them. You know, nowadays when we sit and do nothing for hours on end, we need to give it a special word. We call it meditating or something like that. But back then, that was just life. People just had a far greater tolerance for minimal stimulus. Now, what we as moderns lose in this sensitivity, we make up in free time with the help of our technology. But again, a lot of people back then had slaves, and so they had the free time and the extra sensitivity. This edge, so to speak, this ostensibly inhuman patience and these heightened senses went a long way in fleshing out our maps of the world. In developing humanity's collective body of knowledge. These are the giants upon whose shoulders Newton stood. They were highly perceptive people with sticks and some scribbles. So that's something we need to keep in mind. Alright, so next up we have Archimedes. Born in Syracuse in 287 BC, and died a violent death, I might add, in 212 BC. Archimedes spent some time at Alexandria, like many other great thinkers of his era. You know, there was no internet, so you had to go where the action was at. Some people moved there permanently, others just went there to study and return home. Archimedes was one of the latter. So, after he returned from Alexandria, he returned to Sicily and penned down some advanced works on mechanics and mathematics. One of his feats was calculating pi within 0.02% of the currently accepted value. But, you know, where Archimedes' real importance lay was in the further mathematization of natural phenomena. A project begun by Pythagoras centuries earlier. Archimedes wrote a number of complex works, such as one on the spiral. And now, just like Pythagoras, even within his own lifetime, Archimedes acquired a body of mythology around his person on account of his genius in mathematics and engineering. Archimedes' screw, also known as the screw pump, is one of the most miraculous inventions of his. He also invented the crane. He was renowned for his work with levers and is often quoted for saying, "Give me a place to stand and a lever long enough and I'll move the whole earth." It's a great pickup line too. So Archimedes created a model of the solar system as well, and although obviously this doesn't survive, it existed just long enough to be seen and written about by Cicero, though we don't really know much else about it. A device like the Antikythera mechanism comes to mind, which was basically an ancient computer/calendar. You may remember as well that Archimedes is attributed with the famous saying, "Eureka! I have found it." And all this, of course, was when the local king wanted him to test for the purity of the gold in his crown to make sure that he hadn't been cheated when he brought it in for repairs. So, while sitting in the bath, Archimedes realized that he could tell how much volume a thing was by measuring how much water overflowed when it was placed into a filled tub. So he could individually measure the crown, the pure gold, and pure silver, each in a tub, and figure out that the density of the crown was closer to that of the silver than that of the pure gold. Sure enough, the king had been cheated, and I assume the guy who fixed his crown wound up on a spike somewhere. In any case, near the end of Archimedes' life, when the fleets of Rome reached the island of Sicily, they besieged Syracuse from 215 to 212 BC. The legend goes that in order to repel their ships, Archimedes had devised these sorts of giant mirrors on the walls of the city, and these were used to focus light and burn down Roman ships. It's worth noting that all attempts to replicate this, at least that I'm aware of, have focused on igniting wet wood and not the dry, thin sails, which would go up quickly along with the ropes and then pose a huge risk to the men below on the deck, especially if the mast falls. Even then, however, I don't think that this is true, or, evidence of ancient aliens or anything like that. I think this is proto-sci-fi, literally. Fiction about and or incorporating scientific concepts or natural philosophical concepts. Guys like Archimedes were the intellectual giants of the Hellenistic world. And so in the same fashion, Einstein or Nikola Tesla accrued a large body of mythology around their persons within their own lifetime, so did these guys. And this was a pre-Enlightenment thinking society. So Archimedes dies during the siege of Syracuse. He was killed by a Roman soldier, despite orders that he should not be harmed. This, of course, could just be Livy's pro-Roman apologetics. What are the chances that Marcellus knew of this one scholar who vexed his attempts to take the city in Rome's greatest crisis, and on top of it all wanted him spared? It doesn't really add up. But anyhow, the legend goes that he was on the verge of some kind of great mathematical discovery when some Roman soldier barged in, and Archimedes ignored his commands. So the soldier slew him. Cicero describes visiting the tomb of Archimedes, whose ornament was a sphere and a cylinder of the same height and diameter. Archimedes had requested this to be placed on his tomb to represent what he thought was the highest of his mathematical accomplishments. That is, that the volume and surface area of the sphere are 2/3 that of the cylinder, including its bases. Now, I just want to highlight the importance of this choice for a tombstone before I move on from Archimedes. Of all the things he invented, it was this discovery of an abstract principle, a universal constant, which mattered most to Archimedes. It was not the production of his practical discoveries like the crane or the screw, no matter how useful they were. Just let that sink in for a while. Think about what that tells us of the intellectual climate of the Hellenistic world. Alright, so moving on, we're going to discuss Hellenistic astronomy. Observational astronomy, as we've discussed since the beginning of the lecture series, had been practiced by the Babylonians and by the Egyptians for millennia. The Babylonians had these huge clay tablets with eclipse observation data, and these were very useful for the Greeks. The thing is, as far as the extant sources can tell us, it appears that all the Babylonian and Egyptian works on the subject lack a unifying explanatory framework to explain the motions of the celestial bodies. What the Greeks gave to the world was an application of deductive reasoning to construct a picture of what the cosmos actually looked like. Let's not forget that the so-called pre-Socratics, many of whom studied abroad in places like Babylon and Egypt, even these guys had fairly rudimentary conceptions of what their universe, let's say, objectively looked like in mathematical and not mythological terms. I'm not saying people didn't have functional maps of meaning or working models of how the world functioned, but these were never coherently expressed in so-called scientific terms. Obviously, Ra was the sun, and Set was the midnight sun, and the 7 gates of Ishtar were the 2 luminaries and the 5 visible planets, also known as the 7 planets. But this isn't the kind of stuff that I'm talking about. I'm talking about measurement. It's trying to explain what we literally see. Alright, so the story goes, and there's reason to believe that this is actually how it happened, that a challenge went out from Plato himself while he was heading his academy at Athens. The challenge was issued to his students, and this would have massive implications, because many of the people I'm about to discuss all had connections to Plato's academy in some way or another. Of course, this was all long after Plato's death, which was in 338 BC. Anyhow, in the Timaeus, which is required reading for all of you, he says that the planetary motions are, quote, wondrous in their complexity. But what Plato wanted his students to do was to explain that complexity in simple mathematical terms. This was a big part of the Platonic project, to reduce the ostensibly chaotic motions of the planets to complexes of universal truths. In other words, do the planets only seem to be complex in their motion because of our personal perspective? And if so, is there some kind of simpler truth laying behind it all? It's worth noting here that the word planet means wanderer from the Greek planao, because the Greeks who named them didn't know that they had a fixed course. Alright, so here I'm going to break down a few basic astronomical concepts, and I suppose they're astrological as well. This is kind of a false dichotomy at this point. I need to cover this before moving on to further discussions. There are 3 main celestial motions that I want to talk about. The first is the diurnal motion. You could call this the daily motion. It's the motion of everyday celestial bodies rising in the east and setting in the west. This is the easiest one to recognize if you look up at the sky and it isn't blotted out by break dust or light pollution. The sun, the moon, the stars, the planets, they all move from east to west. Okay, so next celestial motion I want to mention is the annual motion. Some constellations are visible in the winter, and some constellations are visible in the summer. You can see this in motion because a star rises slightly earlier every night. So it appears as if the whole celestial sphere, what the ancients called the first mobile, the very backdrop of night upon which the stars were but perforations, the first mobile seemed itself to rise in the east and set in the west, making one full revolution in a year. Alright, so the last motion I'll mention here is the motion through the zodiac. Now, the planets don't just bounce around the sky all willy-nilly. They're restricted within a narrow kind of band, and it's within this band that we get all the signs of the zodiac, because obviously there's plenty of other signs in the sky that weren't part of the zodiac. 12 were selected because they were part of this band. But here's the thing. This whole band moves backwards from west to east at a variable speed. So with the exception of the sun and the moon, it would sometimes appear like the planet would stop in the sky, turn around, and go back the other way. This is where what was called retrogradation began, and it's often associated with ill omens in astrology. Astronomically speaking, when a planet is in retrograde motion, it appears to make a little north-south loop, and this was eventually called an epicycle. So there you have it, basically. The planets are subject to these motions, so from the ground here on Earth, it appears like they're moving at varying velocities, varying directions, spiraling through the zodiac. And part of the Platonic project was to disentangle this mess and see what was really going on. The apparent chaos really rubbed the Platonists the wrong way, since it didn't fit their preconceived notions of how the world ought to be. So they tried their best to make it fit. There was a great drive among the Platonists to mathematize the cosmos. One of Plato's disciples who took up his challenge was a guy named Eudoxus. His works are no longer with us, but their contents were saved insofar as Aristotle took up Eudoxus's ideas. Aratus's poetic epic, The Phenomena, was an adaptation of Eudoxus as well, and this, while fragmentary, has numerous quote-unquote translations in Latin. Now, Eudoxus's model consisted of 27 concentric spheres, each moving at different speeds, with the Earth immobile at the center. The outermost sphere carried the stars east to west. This again was the first mobile, the primum mobile. So the planets each had their own spheres with an extra sphere for their epicycle. Then the sun and the moon had a combination of spheres, one for diurnal motion, one for motion through the zodiac, and one for that north-south wobble through the zodiac. Now, by and large, this model did quite a lot to make astronomical predictions. It was a functional model. But since it wasn't perfect, it failed in two critical ways. First off, it didn't account for the fact that the planets appear to change in brightness as they move through the zodiac. Secondly, it didn't account for the fact that the seasons are different lengths. Summer is longer than winter. Well, to remedy this, other students of Plato's Academy tweaked this system. One of these people was Aristotle, and what he did was add more spheres to try and correct it. Anyhow, lots of people tried their hands at this, and there proliferated a great number of models which had increasingly more and more spheres to account for all the little bugs people had in reconciling the map with the territory. Ultimately, however, they did what they set out to do. They set the groundwork, in answering the Platonic challenge, for the reduction of a complex of ostensibly irregular motions down to its underlying mathematical simplicity. And, of course, this project was not thoroughly completed until Isaac Newton discovered gravity, and arguably that project continues. I mean, scientists only confirmed Einstein's gravity waves last year, so who knows how far that rabbit hole goes. Obviously, the strength of science is that it is provisional, something which the anti-science crowd likes to level against it as an insult. Which brings me back to my thoughts the other day on flexibility versus robustness, with strength being found somewhere in the middle, not at the ends of the pole. Ultimately, what Eudoxus did, and this is a Greek idea, was he, quote, saved the phenomenon. They didn't scrap the model because it wasn't 100% accurate. They didn't make the good the enemy of the perfect. No, what mattered was saving the phenomenon. That is, describing what it is that we actually see. And you know what? That was good enough for many centuries to come. Now, there are two discoveries which were made in the Hellenistic world which I want to discuss here. The reason these two discoveries are so important is because they are discoveries which were actually true, but were rejected by the science of the day. The accumulated body of knowledge, coupled with tradition, could not allow these two discoveries without the whole system crumbling apart. One of the brilliant students at Plato's Academy, Heraclides of Pontus, had suggested to do away entirely with the diurnal motion of the heavens, and in its place, he wanted something more elegant: the daily rotation of the Earth upon its own axis. Now, another famous innovation by Aristarchus of Samos, 3rd century BC, was that the Earth orbited around the Sun, and not vice versa, as was held in the Eudoxian, Aristotelian, and eventually Ptolemaic system. Now, we may have a hard time wondering why they didn't accept these truths as patently obvious immediately after they were posited, but if we put the notion in context, it's clear that these discoveries were rejected because they conflicted with the pre-existing functional model of how the physical world operated. These two little factoids would have thrown a wrench into the whole system of Hellenistic astronomy and require that everything be built again from the ground up. If the Earth was not at the center of the universe, then how did it just hang in space? Why did the water sink to the bottom, the Earth hover atop it, the air above that, and then the fire above that? Why did everything ostensibly rotate around the Earth? All of this stuff just went against common sense. Think how fast the Earth would have to turn to rotate on its axis every day. We'd all fly off. So, what I'm trying to say is this. Oftentimes, there are discoveries made about the objective world which are promptly rejected because they do not fit the working model of the times. Whether it's on account of tradition or authority, some discoveries just get pushed to the wayside and are never heard of again. It's fun to imagine, and trust me, people do it a lot, what other kinds of things were discovered in the ancient world which were actually true, but yet were not accepted on the grounds that it would have destroyed the traditional way of looking at the world. That being said, let's not judge our ancestors too harshly for wanting to stick with what worked and what jived with their common sense. For Plato and his immediate intellectual descendants, the computation of physical, astronomical phenomena was, as I've been alluding to, part of the project begun by Pythagoras and taken up vehemently by Plato. The end goal of this project was to reveal the intelligent design inherent in nature. This is the concept that underlies the Timaeus. The whole world is design. The demiurge created it by looking at the forms, thus imbuing the world with mathematical harmony. So, all we need to do is look at the world, and that mathematical harmony will become apparent. To explore the world mathematically was practically to explore the mind of God. The Platonic project, if you will, was to put the cart before the horse. to put the map behind the territory, to put the essence before the existence. And this, for good or for ill, would have massive ramifications over the face of the whole globe. It is to say, in the beginning was the Word, and then to work one's way backwards. And to me, this Platonic project and its long-term effects upon the world, this is the real core, the nut, if you will, of everything I've been discussing throughout this lecture series. I'm not here to condemn it, nor to praise it. I'm here to point out who, what, where, why, and how, and to show that there is also a polar opposite view to this project, one whose primary texts were largely left uncopied. And the dialectic, the struggle, if you will, between these two modes of thinking, that is, between idealism and realism, would shape the whole of the Western intellectual tradition up until the present day. Platonism infects nearly everyone in the world to some degree, and that is not a bad thing per se, unless you cannot see things without the use of that lens. It then becomes pathological. To only see the world through that lens is what Jean Ray, the crazy time cube guy, calls monist death math. And I applaud him for the term. It needs to become a meme or something. If we want to get all teleological, Platonism was a stepping stone toward modern science, but one which ultimately had to be relinquished to fully make the jump. Kepler was one of these guys who could never quite make the jump, and an artifact of this is his publication of a Platonic solid model of the solar system in 1596 called the Mysterium Cosmographicum. Go read about that. It's quite fascinating and one of those, I wish that's how the universe worked kind of things, but ultimately it was Platonism writ large, and so it was fundamentally flawed insofar as it chose, key word here, to put the map behind the territory. Now, it was entirely their right to do so, of course, do what thou wilt and all that, but it would cause them problems in adequately explaining the nitty-gritty details of reality. And as the idiom goes, the devil is in the details. You can't land a rover on Mars with good enough, as NASA learned in 1999 when it lost its $125 million Mars Climate Orbiter because contracted private engineers failed to convert from English to metric measurements when they were exchanging their data before the craft was launched. You can't land a rover on Mars with good enough. Alright, well, I think that covers what needs to be said for today. When we return, we'll probably be covering the Third Punic War. For now, you've been listening to Encyclopedia Hermetica, A Big History, and I'm Dan Attrell. Thanks for listening.